Hey guys, welcome back to my YouTube channel. So as promised, this is a teaser for the CAPE Chemistry Unit 2 classes. There's still space, so you can join. Contact me. Alright, so I'll be going over what we did last week because you weren't here, Anicia. So yeah, we're going to that and then go into what our actual lesson for today. Sometimes we'll go for 1 hour, 1.5, sometimes 2. I hope that's okay with you because by right, you get two. You're supposed to get 2 1-hour sessions each week, right? So it's basically based on whenever we are free, all right? All right, great. So let me share my screen. And you can always feel free to ask any questions if you have any questions. Okay, what are you seeing there? The classroom. Okay, let me just save this real quick. And here we go. Boom, 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 boom. All right, pick a color, any color, anybody. The first.
Green.
Green. All right, green it is. Okay. So last week we dealt with, give me a second, I'm hot. Last week we dealt with properties of carbon compounds as well as hybridization, the process of hybridization, and we did a bit of compound naming, and we spoke about we spoke about homologous series and functional groups. So just going to do a quick run through of that again, and then we're going to deal with solving empirical formula questions and as well as the molecular formulae questions. All right. So when you were here, so I'll be asking you a lot of questions. What's catenation?
Catenation basically is the ability of carbon to bond. Is basically the ability of carbon to bond
With other carbon compounds. Very good. Not other carbon compounds, other carbon atoms. Sorry. So that can be straight chains, like in the case of ethane. Remember I said that?
Yes, you did.
Can also be branched chains like this, CH. Right? And we can also have ring structures like benzene and cyclohexane. So benzene, cyclohexane. Cyclohexane is a 6-carbon ring. Remember, each point where the meet here represents a carbon atom. So carbon, 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 carbon. That's 6. The difference between the benzene though and the cyclohexane is that there are double bonds in benzene, right? So each of this is a carbon. Oh yeah, I told you that I wasn't going to use the thing next week, the PowerPoint, the original PowerPoint, because that was a whole mess and I don't know why I decided to use that. All right, so that's catenation. Oh, and tetravalency.
Sorry, came out for a second. All right, tetravalence is basically the unique property of carbon to have what 4 valencies available for bonding with other elements, including
Tetra meaning 4, valency meaning outer electrons.
Yeah.
So it's the ability of carbon to bond with 4 other atoms, right?
Exactly.
With 4 other atoms. right, so this is a vibe. This is a vibe. You remember it? That's great. All right, so last week, wait, Anissa, is all of this clear so far, right? What's catenation? What's tetravalency? Can you hear me? Wait, you're very low. I'm not hearing you.
But yes, I am understanding so far.
Very good. All right, great. Okay, let me clear this off a bit and then go over to here. So last week I spoke about the normal atomic diagram that you learned to draw in grade 11, where you know your protons, neutrons equal that, and for carbon the amount of protons is equal to 4, right? Is that true?
That's true.
Carbon have 4 protons, miss?
It have 4 outer electrons, but in total they have 6, 2, and then 4 on the outer.
Exactly. So carbon's proton number, Miss Owen, is 6.
Oh, I'm sorry. Okay, I thought that.
Yeah.
Never mind.
I did it to trick you. And then how many neutrons? In carbon 12. What are we talking about now?
Well,
How many
sorry,
neutrons in? 6.
6
Very
for
good.
the total number.
Yeah. So the total would be equal to the total number of nucleons would be equal to the mass number, right? So here we have the first shell, then this. Or is that a lie? Let's use that as the first shell. So the first shell would have only 2. And then the outer shell would be 1, 2, 3, 4, and that would total a number of 4 available spaces to make another bond, right? So an atom would bond there, another atom would bond there, another atom would bond there, another atom would bond there. But let's look at the arrow and box method for the carbon atom. So you have 1s2, 2s2, 2p what?
6. No.
All right, carbon has 6, 4, 5, 6. That would be more than 6. We already have 4, so 2 plus 2 is 4. So basically subtract 4 from 6 to get the number that should go here.
2.
2, very good. So let's look at the arrow and box method. Let me go to into share to make this clean. All right, 1 box, and this would be our 1s orbital. Then this would be our 2s. Well, that's a disgrace. Great. And that would be our 2p. All right. So by Aufbau's principle, you know that we fill the electrons having the lowest energy first, the lowest energy spin, then we pair them. So that would be 2 electrons for that. The 2s orbital would have 2 electrons as well. Then you'd have 1, 2. Now, we don't see how carbon would be able to make 4 bonds here because this is completely empty. Then this would be eligible for pairing. This would be eligible for pairing, right? But we can't just drop 2 electrons right here and it's like go, because then that would be opposing Aufbau's principle, right? You have to put them singly first and then you pair the electrons. And that's one of the main reasons why.
That's correct, yeah.
Yeah, so that's one of the main reasons why when we were drawing this diagram here, over here, this atomic diagram in grade 11, your teachers told you to write them singly first, then pair them, because that's how we do it. So carbon atoms actually achieve these 4 bonds by a principle called, or phenomena, phenomenon called hybridization. What is hybridization? Do you remember, Owen?
Hybridization is basically where electron orbitals are able to combine with each other in order to form what's the word I'm looking for? In order to form like an equal amount of energy, basically an equal amount of energy orbital that's between the orbitals that they have combined with each other. So
I
for
told you that
example,
yesterday. I told you that the last class. Yeah. They're called degenerates.
degenerates. Thank you.
Yeah.
Important term. Mhm.
So,
Degenerates. Fancy
question,
term. Yeah.
is that where the d orbitals come in?
No. Well, no.
Oh, okay.
So hybridization is where orbitals mix. And in this case, I'm going to show you where the s orbitals mix with the p orbitals. All right. So let me scroll up a bit. So in the case of a carbon to carbon single bonds, those are alkanes, right? So that's the homologous series, alkanes. What you'll see is, let's see, you have your 1s orbital here. Above that, you'd have your 2s orbital. Then above that, you'd have your 3p orbitals, which would be your px, your py, and your pz, right? That would be a 2p of your 2p orbital overall with your p subshells, right? Px, py, pz. Clear?
Clear so far, yeah.
All right. And you have the electrons sitting all tight and pretty like that. All right, cool. Now, what you'll have happening is this s orbital mixing with the 2p orbital and all three, right? In carbon-carbon single bonds. So you'll end up with orbitals, 4 orbitals that are between the energies of the 2p and the 2s, right? And these would be called sp3 hybrids. What sp3 means is that you have 1 s orbital mixing with 3 p orbitals. All right? And whenever you add like 1s plus 3p, that's a total of 4 orbitals. That's why we have 4 hybrids. Okay? And each hybrid would have 1 electron capable of pairing. So that's how carbon is able to make its 4 bonds. All right?
All right, yeah.
So another point, hybrid orbitals or hybridized orbitals, they are able to form sigma bonds, while unhybridized orbitals those will form pi bonds, right? And pi bonds are basically the p orbitals overlapping laterally, right? Remember last year I told you that pi bonds or bonds overall, covalent bonds are formed by the overlapping of orbitals. Clear?
Yes, I remember. I remember that, yeah. Clear.
All right, great. So now would we know if these degenerates would form or fall, right? Would it be closer to the P or would it be closer to the S? How you can figure this out is find out which orbital does it have more of. So in this case, S would be of one of four characteristic in the degenerates, while the P's would be 3 out of 4, right? Can you see how that is?
Yes, miss. Yes, miss.
What's a quarter as a percentage?
Quarter that 25%, and 3/4 75%. So you know it'd be 75. It has 75% character of the P orbital, and it have 25% of the S orbital character.
Very good. So Anicia, which would you think it would fall closer to? The P's, the 2p orbital, or the sp, the s2s, sorry. If the P's is 75% and the S is 25%, would the degenerates fall closer to the 2p orbital or the 2s?
2p.
Yeah, don't ask me, tell me you're correct. Very good.
2p.
Very good. So that's that for carbon-carbon single bonds. Now, what I was saying about the hybridized orbitals forming sigma bonds. Now, seeing that we have four sp3 orbitals, let's say we have carbon here. You will see bonds being represented by single lines, right? These single lines are sigma bonds. Why? They are sp3 orbitals, either overlapping with, say, the s orbital of a hydrogen or the sp3 orbital of another carbon atom, right? So that's that. Now, in the case of a carbon-carbon double bond, each stroke represents one bond. So 1, 2, 3, 4. Now let's say we put another carbon here. This would be a sigma bond, or the top one, whichever one. And the other would be a pi bond. I'm going to show you why no. So let me give you a break-ish, a little breather. Any questions?
No, sorry, no.
All right, no questions. All right. So carbon-carbon double bonds. Same thing, you're going to have s orbitals mixing with p orbitals this time. But instead of the s orbital mixing with 3 p orbitals, you'll have it mixing with only 2, leaving 1 free p orbital. And that's how the pi bond is formed. All right? So let me just write that down or show you visually how that actually happens. So I'm going to draw it back. So you have your 1s, even though this is unnecessary at the moment, 2s, and you have your three p's, 2 p's, which is your px, your py, and your pz. All right. This has 2 electrons. This has 2 electrons. This has 2 and 1 blank. Now, how many hybrid orbitals would form if you have a 2s mixing with only 2 p orbitals?
Repeat the question.
How many hybrid orbitals would you have if you have 1 s orbital mixing with only 2 p orbitals?
Will it be 2p2?
I'm not hearing you.
Will it be sp2? Sorry.
Yeah, it would be sp2 hybrids. But how many sp2 hybrids would you have?
2, I guess.
3.
Have 3 of them because that's 3
Oh yeah, because
orbitals.
1 s,
Yeah, you have 2. You have 2 p orbitals. You have 1 s orbital.
1 s.
Yeah.
Yeah, great. So it's 3. So you'd end up with 3 sp2 hybrids. And I guess you can, seeing that it mixed with 2, you can just take out the 2, right? Let's say we're going to just erase those 2 and not think about them anymore. So there you go. Don't really think about this either. Then you have 1 electron. 1 electron from the 2s would come. The other electron from the 2s would come here. And the 1 electron from the one that had its own electron would come here, right? So basically, what you'd see happening is if you have the 2s orbital here and the 3p orbitals right here, you would have one of the s electrons being promoted to this empty space. All right? So that's what happens. So that's how we end up with the 2 sp2 orbitals. All right? So here, as I said, hybridized orbitals will form sigma bonds. So these would be 3 sigma bonds. And then we have an unhybridized orbital here. This would give you a pi bond, right?
Yes. So the unhybridized one gives you a pi bond, while the okay. So that single p orbital that wasn't included in the degenerate to just form the pi bond. Okay.
Yes, by overlapping with another p orbital from the other carbon that will bond to it. So this carbon atom would be sp2 hybridized, and so will this one, sp2 hybridized. So it will always have 3 mixed, or let's say 3 hybridized orbitals, which would form the sigma bonds. So you'd have, let me see if I can highlight this. This would be a sigma bond. This would be a sigma bond. One of these would be a sigma bond, right? For this carbon atom over here, right? And for the other carbon atom, this would be a sigma bond. Would you look at that? This would be a sigma bond. This would be a sigma bond. And whichever one was the sigma bond for that would be another sigma bond for this one, right? That leaves you with 1 pi bond here. Clear?
Clear.
All right. So for the alkynes, that's carbon to carbon triple bonds. So these, I forgot, did I tell you what the carbon-carbon double bonds are? Those are alkenes, all right? Carbon-carbon double bonds, alkenes. So these alkynes, carbon to carbon triple bonds. All right. Now these have 2 pi bonds. Pi bond here. And a pi bond here. And one of these in the triple bond has to be a sigma bond. So in a triple bond, you have 2 pi bonds and 1 sigma bond, right? And the other bond that is left to make the 4th bond with the carbon is a sigma bond. And if you've been picking up the trend, you should see this already. So 1s, your 2s, and your 3p orbitals, px, py, pz, right? So 2p. And put these back, your electrons. I'd be writing very terrible. All right. What you'll have is the s orbital mixing with only 1 p orbital this time, and it would be the one out here, the pz, that's empty. So you'd have one of these electrons being promoted to the pz, right? So if you have one s orbital mixing with just one p orbital, what hybrid would you get?
An SP degenerate.
Very good. sp orbitals. Orbital.
Can I call it degenerate, or that incorrect to say?
You can call it degenerate. Yeah. Degenerate is an adjective though. So degenerate orbitals.
Oh, gracias.
De nada. So how many hybridized orbitals would you get?
You will only have two because you only have one s orbital and you only have one p orbital.
Very good. And you see how we got the two?
Yes, I did.
All right, very good. So 1, 2. These are sp, sp, each with one electron. So that leaves you with 2 hybridized orbitals and 2 unhybridized p orbitals, right?
That's true.
So
those
another,
two p orbitals. Oh, sorry.
go ahead, Owen.
So those two p orbitals will form a pi bond, right? With another.
Well,
Right.
2 pi bonds, not one pi, not a pi bond, but each would form a pi
Two pi
bond,
bonds.
resulting in 2
Great.
pi bonds. Yeah.
Thanks.
So that's how we got the 2 pi bonds over here with a sigma bond, with 2 sigma bonds, one sigma bond here and another sigma bond amongst the triple bond here, right?
Right.
All right, so this hybridized orbital would give you a sigma bond. Then you'd have 2 pi bonds in the triple bond. And then you have another resulting sigma bond over here, or you could put it here or here, it doesn't really matter. But you'd have a single bond that could bond to anything else but another carbon, right? It could be another carbon as well, right? As long as it's not a triple bond. Was that clear?
That is clear.
Yes, it was.
All right, great. So that's how hybridization occurs. I'm going to ask you guys to explain this soon. All right, so apart from that, what else did we go through last week? Homologous series and what? Functional groups, right?
Yes, we did that.
Can I clear this off? You have it?
You may clear it off, yeah.
Okay. So what time is it? So I'm going to go through this part. Then a part of, do you want me to do isomerism first or the empirical formula? Since I'm giving you that for homework.
Empirical.
All right, so I'll do that before I do isomerism. Okay, and then we will work on the labs, all right? So,
All right.
Both of us have labs?
yes, you both have labs. But you said your teacher started at you said your teacher started at what? Module 2, so you guys have 2 different labs. So I don't know. I'll probably put you in breakout rooms or not. I just told you, so I'm gonna see why I'm gonna put you in a breakout rooms.
Plus, me can learn from Owen lab to suppose me get the lab there. You know?
You'll probably get it because
learn
our
from-
famous calibration prepared lab. You probably no game most likely because
that lab took me all day, bro.
Kuya, I'm gonna start it. No sir.
Doing the actual lab, Owen, not writing it. Not writing it. Doing the lab took me
like
all
them
day.
PD.
Come here, if you take it the whole day, I say it'll take me one whole day plus one other day.
It's not. I know.
I not even know which
day. I know
which
why it took
module
me
is
all
that.
day. Module 2, you're gonna learn what we did learn.
No, as in me, I said me not know what my teacher start teach. with a module 2 or 1 hour. The man just come and give work and teach half of the work when give. So like when I give past paper and then teach half of the past paper.
No, that's not a bad strategy though. I think that's the method I use when I have students who have exams coming up earlier than usual, like January, starting September, have exams in January. Teach them from the past papers.
And then we have 4 PD as way. God almighty. God guide me.
Come, you want the dry labs too?
Yes, miss. Everyone, Owen, all of them. I'm going to vet them before you submit them. All right? All of them.
Yes, I did right now for me again.
All right. Okay, so let's move on so I don't make this video too long. It's unfiltered, by the way. I'm not going to edit it. All right, so hybridization is what we just did. Another thing is resonance. Resonance occurs. All right, let's talk about that a bit. Now, last week I said, skip this, skip that. Yeah, benzene can look like that. Benzene can look like this. The thing is, we don't know exactly where the double bonds in benzene are, right? So that's why we write them, draw the structure like this with a circle. And I said it was called Kekule's structure. And it's called a resonance hybrid. Or these are called resonance hybrids, right? So in like a carbon-carbon single bond, the electrons are localized in this area where the bond is. Carbon-carbon double bonds, the electrons are localized here, and it doesn't allow free rotation. That's the thing with double bonds, no free rotation. And that will come up more when we're talking about isomerism. All right. Here, on the other hand, we don't really know where the electrons are, so we say they're delocalized. So it could be here, it could be here, could be here, could be here, could be here, could be here. Could be anywhere in there. Oh my God, I just marked this up. Yeah, but that's the thing. So electrons in these bonds are localized, while in, say, this structure, they are delocalized. Cool?
Cool.
All right,
Yeah.
great. That's all you need to know about that. You don't need to know how to explain anything else until we get to actual reactions with benzene. But let's hold off on that for now. All right.
So, only thing I need to know is that from time to time, the electrons within the benzene structure is going to change their location because of resonance. That's all I need to know.
Resonance. All right. So, homologous series. What are homologous series? Anybody can take it, if you know.
They have,
nobody? Okay.
similar, I believe it's hold on there. No idea. Hello?
Yeah, I'm here. I'm waiting.
Hola.
Oh, okay. They have similar chemical properties and share same general formula.
Very good. So that's a property, or those are properties. So homologous series, they're a group of compounds that share the same functional group, right? So that means they'll have the same not structural formula, general formula. They'll have the same chemical properties. What else about them? Owen, tell it is. Was it last week? Yes, I told you it's last week.
Give me another property of them. You want another property, Camille?
Yes, ma'am.
My mind is blank, to be honest.
That's fine. That's fine. Let me remind you. Remember the increase by. Yeah, go ahead.
I was asking if these are the same ones that they have common general method of preparation, like them basically can prepare the same way.
Yeah, they have the same chemical properties. I don't see why not. Yeah.
Okay.
All right. So let me write. I'm left-handed and this thing, I need to change the settings on the tablet. It's set for a right-handed person.
Guys.
All right. This spelled correctly. All right. Homologous series. First of all, same general formulae, right? For formula, let's say formula. Number two, same chemical property. Ensure you're writing and not screenshotting, please. Coming from a past student, I know how that screenshotting thing goes, so make sure you're right.
No, I'm actually want to set up note in a place where the notes are going to look orderly. So I'm going to have to separate this unit from this module from modules using that it have uncertainty.
Oh
So I'm
yeah,
going to
yeah.
have to fix that.
Can take your notes digitally here then. Type them up.
Yeah, so since they're recording that, I'm going to have to go through and then write it down properly in the orderly way. Since I'm getting half term coming up, I'm going to use that time wisely to fix up the notes.
I love to hear that. No procrastination. We're working on that this year, Owen.
Yes, a goal. Yes, a goal of mine.
Yes, ma'am. So, same chemical properties. All right. Successive units increase by CH2 units, remember? I think that's what I said, yeah. Successive molecules are, yeah, let's say molecules. Increase by CH2 units. What I mean by this, let's use methane, for example, CH4, right? That's methane. Ethane would be C2, H6, right?
Yeah, man, following you.
It add one carbon and two hydrogens.
Oh, that makes sense. Oh, me see pattern.
Yes,
Methane
miss.
already have CH4. You know, the people always say so we never really pay attention to what I mean.
No, you know. We're increasing by CH units, CH2 units. So tell me, the third one would be propane. Pro is for 3. So meth 1, 2, 3. Pro, pro 3.
Again, feel so nuts.
Same.
Propane.
C2H8
C2, you sure?
This will be
C4
C3.
C3. Yeah, add one carbon to 2. So
Oh,
C3.
one carbon and then 2. Okay.
Yes. So the next
So
one would
add
be
2 to the 6.
butane. What would this be?
C4H10.
Very good. You see, you get that nice
Thank you.
and quick.
Cameo-Lee. Don't say a star. You are.
Actually, I start for real.
All right, so I think I'm gonna get this. Try pentane. Pentane. 5. Pent. The suffix, the prefix rather is 5. Pent 5. But 4. Prop 3. Eth 2. And meth 1. So what would be pentane?
C5H12.
Very good. So that's another property of the homologous series. They increase each molecule or member of the series. It increases by a CH2 unit. Now, let's say the other property, as per the physical properties of the homologous series, they increase in a regular way. And what I mean by that, or change in a regular way, is like, let's say methane. Methane is a gas, right? As the chain gets longer, the compound gets denser, right? So the chain, it will change its state, meaning it will change from gas to liquid to solids, okay? So that's another thing you can use to think about properties changing, because let's say a gas is less dense than a liquid, right? And I can show you why that is.
I have more space between here.
Yes, that's exactly why. So
Sorry,
remember,
one
yeah?
question. So would it be okay to assume that these homologous series will behave like group 7, because you know group 7 they have like gas, then liquid, then solid. That's the general. That's
Yeah.
generally how we
If you
are.
want to make that analogy, it's correct. Yeah. Hello.
I'm here still. I'm here.
Okay, so the particles in a gas, they're far away. I think this is even too close. Then you have liquids. They're closer, right? A bit more compact. And solids, definitely in a crystal lattice, correct?
That is correct.
All right. So remember, I was telling you that if you have a container, you want to think about density of having a higher concentration. Because a higher concentration, that means that the particles are more dense in a specific area. So here you have doom, particles, particles, particles. They're highly concentrated over here and thus highly dense in this region, right? It's the same thing when you talk about diffusion, you know. Let's say you spray some perfume right here. All the perfume molecules will be concentrated right here. Then they'll spread out, right? So that's where we have particles in a higher region moving from the higher region that they're in to a region where there is less of it, meaning lowly concentrated or less dense, right? So gases being spread apart, the particles of gases being spread apart so far makes them less dense than liquids, and thus liquids less dense than solids, right? Yes, Cameo-Lee, I understand.
Cameo, yes.
Why? And I have me here sit down like anybody there? My Wi-Fi chip out or something?
No, ma'am, we're hearing you
I'm
loud
so
and
sorry.
That's fine, that's fine, man. So you think you're understanding everything so far? Any questions?
No, ma'am.
so far everything good. I got we revised the catenation, tetravalency, we did hybridization, and now we move on to the properties of homologous series. And now we are basically making an analogy to it. So I think I'm fine, yes, so far.
All right, great. So let's talk a bit about I'm going to tell you the major ones, and then I'll give you a sheet with the others, all right? So the homologous series, I'm gonna just put homo series. That sounds weird, bro. The functional group, all right? So first one, alkanes. These consist of carbon single bonds, and they are called alkyl groups, right?
Yes.
Alkenes, carbon double bonds, alkenyl. feel like I should know this or not, but I never found it. I always looked for it, but I never found it. See, carbon-carbon triple bonds, alkynes, right? Functional group, carbon-carbon triple bonds, and yeah. Then you have alcohols. Functional group is an OH group, right? R groups meaning rest of the molecule, right? So you can attach R groups to these as well, but let me not. So the alcohol are OH groups called hydroxyl. Then you have the C double bond O group, that's a carbonyl group. And carbonyl groups are found in aldehydes and ketones. Now, the difference between aldehydes and ketones is that aldehydes, along with the carbonyl group, has a hydrogen atom attached to it, while ketones only have the carbonyl group, right?
I always saw these when I was in bio, but by unit one though, I always had the aldehyde and ketone, but I never really understood them. I just swatched some stuff about them.
Yeah. When you were learning carbohydrates, right?
Yeah, I was learning carbohydrates.
You know, I should know this. Like my lecturer been saying this in class. Like you have aldose sugars and ketose sugars. I think, oh Jesus. Look at the future doctor not remembering.
What's the word before? The ketone?
Aldehyde. Let me write it properly.
And alkenes, alkyne are the third one doesn't have the name for the functional group.
All right, I'm gonna go off on limb and say glucose is a ketose sugar. Is it? Or is it fructose? You know what? Never mind. Never mind.
Wait,
I'll
you
look
mean
for
the
it
one?
later. Yeah, go ahead, Owen.
You mean the one where you have two different sugars? We think of fructose. I think of fructose because I remember from me something lab, not lab, but from unit one, fructose have this thing about it. I could bring up my unit one textbook to see it, but I'm pretty sure it's fructose. I sugar, I try to remember.
Yes, it is fructose.
Fructose is a ketose sugar, yeah.
Yeah.
And glucose, galactose, all of them, the other ones, I think xylose, some names, mannose, those are aldoses. Yes, I think. All right, I'll check it. I really should be confident in my knowledge, seeing that I just took an exam. But all right, so that's besides the point.
Cameo.
But I know this how we carry results.
Girl, and that's me. Come here, ask me what results there. Don't ask me what results. We're not going to speak about that topic, okay?
God go with me.
Oh, and please don't make me call you and ask you about your results. Or I'm going to malice you for the rest of the school year.
Let's no. I'll definitely tell you. I'll tell you.
What else did we go through last week? Structural formulae and what? Just that's left, structural formulae. Because I said I'm not going over the naming compounds part because I'm not ready to teach you that. I want us to do isomerism first before I teach you how to name compounds. Okay?
Okay.
All right. So let's do the structural formulating and then we go to the. I cut the video because I'm past the time. I always go over the time. I cut the video, teach you how to do the empirical formula, molecular formula, and stuff, and then we do that. Oh yeah, and remind me to do the outro, please. Oh, when I didn't do an outro last week.
I will definitely remind you.
All right, so structural formulae. They show the arrangement of the atoms in the molecule, and you can divide that into displayed and condensed, right? Also skeletal, but that's not on your syllabus, so I'm not going to teach you skeletal formulae. I'll probably give you some examples, you know, some practice questions just in case CXC decides to pull a full 180 on you guys. Because I'm sure one question will come from my exam this year in a different syllabus. Well, let me not say I'm sure. I just don't know about it. First I see it in my life, but I didn't panic. I took a deep breath and wrote back the instructions in the blank spaces.
Cameo-Lee, I need help.
With?
I have a test the 19th on volumetric analysis and gravimetric analysis. And objective 1 of 3.
You're sorry, module 2?
When is the 19th?
The 19th to the 9th. The 19th is the week after next Tuesday. So I need for ready for that. Can't feel.
I'm saying you not get midterm.
Oh,
Oh wait. My midterm, I work at school with you. Not
Displayed, condensed. I don't get midterm, I'll be at school.
So yes, I'm just putting it out there from now.
Yeah, all right. So the 19th is not next week, but the week after. So
yes.
All right. So next week is going to be a longer class, all right?
Okay, no problem.
So send me the topics. I'll send you some prior reading to do, and then we go through it, practice questions and all right?
All right.
All right. All right, so displayed formulae. The displayed formulae shows exactly where the atoms and the bonds are, while the condensed formulae just show you. Let me just show you. The condensed formula doesn't show the bonds. That's the difference between the displayed and the condensed. The condensed doesn't show the bonds, while the displayed does show the bonds. And remember, the bonds are the lines, okay? So, for example, in the case of ethane,
I have a question. Why they all represent like carbon atoms like as pentagons or hexagons?
because they're ring structures, also called aryl compounds, ARYL compounds. Aryl compounds are ring structures, so
I remember by a word orange time.
4 carbon rings. I don't know why I'm doing this. So you have 5 carbon rings, like here, C, C, C. So each vertice, these are what they're called, right? I'm not that. I don't remember this geometry thing from whichever grade I learned this in, but that's it. Each point here represents a carbon atom. So like in here, this is cyclohexane. Each point is a carbon, right? Answer your question, Owen.
Yes, you did. Gracias.
No hay de qué. So H, 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 H. All right, so this is a displayed formula. So you can see the bonds, the actual bonds, right? Represented by the lines, correct? And let's see.
Yeah.
This is what? Ethane?
Yes, miss. Alkane with 2 carbons, ethane. No double bonds, all single bonds. It's an alkane, thus it's ethane. All right?
Correct.
So the condensed formula would be CH3, because on this carbon, you have 1, 2, 3 hydrogens and another carbon attached. So you'd put another C. Then to this carbon, you have 1, 2, 3 hydrogens. So H3. So this is telling me that on this carbon, I have 3 hydrogens and 1 carbon atom attached. And on the other carbon atom, this carbon atom, I have also 3 hydrogens and 1 carbon attached. Okay? So that would total the 4 bonds. Understood?
Understood.
Yeah.
All right. Me telling you this is just half of the story, you know. You guys going to have to revise and practice these things. All right. If you don't practice, you're not going to get it. You're not going to remember. All right.
That's true.
So I'm using strictly examples. Let me not say strictly examples from the book. I'm just going to use this other example from the book because it's easier than if I just make one from my head. All right. I think Owen knows this. So I'm gonna give Anisia a try at this. The condensed formula would be CH3, right? Because they have 1 carbon, 3 hydrogens, then another carbon, 2 hydrogens this time, 1, 2, and another carbon, 2 more hydrogens, then nitrogen, and 2 hydrogens. Clear?
Clear, ma'am.
Yeah.
All right. So let me suppose you're given this one. Say Br, H, 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 H. What would be the condensed formula for this, Anisia?
CH3,
Mm-hmm.
CH2,
Mm-hmm.
uh, C. Would I write the other CH3 first, then you put the BR?
No,
Or
write it in the order you
just
see
say
it.
it as it is?
Say it as it is.
Okay,
The
so
order you see
CHBR
it. Mm-hmm.
or CBRH,
Mm-hmm.
then CH3.
Yeah. Don't ask me. Tell me. Because you're correct. Very good.
CH3. I was thinking there's some order thing, but
Just write it in the order you see it, man. Don't change it. Remember, you're telling them exactly how the structure is drawn, right?
okay.
Yeah. So, you think I get that? Or you want another one?
I think I get it.
Yeah, I'm going to give you another one. That did sound shaky. So,
Let me do this.
all right. Try this one.
Hold on, put back. Oh, yeah, clean it.
Tell me when you're ready.
Oh, hold on. Let me just. I think I'm gonna.
All right. Okay. Let's say I give you this. BR, BR, H, H, BR. Yeah, I'm going to do that. Yes, definitely going to do that. All right, what would be the condensed formula? Let me give Owen.
CH3.
Give me a sec. Let me give Owen one as well. Is even possible? I don't know if it's possible, but everything is possible through Christ.
Amen.
Let me not be a garbage person. Ready, Anisia?
Yeah.
Mm-hmm.
So it would be CH3,
Mm-hmm.
CBR2,
Mm-hmm.
CHBR. No, CH2BR.
Very good. No, Owen.
Alright, CH3,
Yes, ma'am.
HCl,
Hold
H.
on.
Mm-hmm.
Go again.
HClH.
Mm-mm.
Isn't
Wait
that
there.
Cl up there?
Yeah, but you know say H first. Remember, you have to tell me what's
Oh,
bonded to the carbon there.
CClH. Sorry.
Yes, miss.
CClH. All my mind, I thought I said it. Honestly. And then
I
now we're
think
going
I
to have,
think I think because they're so used to the hydrochloric acid, that's what came out.
yeah, true.
They almost passed me. All right, continue.
And then now we're going to have C CHF. CF. CHF.
Mm-hmm.
Oh, put the F. Okay. Alright.
It doesn't
And
matter.
then
You
now,
can put anyone first.
okay. Thank you. And
It's
then
just
now we
less
have,
awkward to put the H first.
oh, it's because I've been going in a pattern on my mind, just going at the top and then going on the bottom. That's why.
That's fine, no problem.
And then now we're going to have CH3.
Yeah, very good. So congratulations to you both. You know how to write the condensed formulae for compounds now. Well,
Yay!
straight chain compounds.
Interesting.
Nice.
So we're going to do a single branched one, and then I'm going to show you ring compounds, and then I'm going to cut the video, and then we're going to do the empirical formula. All right. I have a slight headache, bro. So probably won't go for 2 tonight. We'll probably pick up on another day. We'll see.
Miss, oh, sorry. Come. What do you call it? A retrospective
Timetable?
timetable?
Yes.
The one without time?
Mm-hmm. What
I've been
about
u-
it?
I'm using it and it's going good. It's going good for me. But
That's
I'm going
great.
to like 2 subjects easy because I don't know 2 subjects because
That's a good plan. That's a good
yeah,
plan
like
then.
2 until I can take up 3.
All right. Yeah, you have to start small first. Like it's like weaning a baby. You can't just stop giving the baby milk. That's going to be a problem. You have to take time and take them off, right?
You're right.
It's
Thank you.
like if you have a person coming into your clinic with, let's say the person is obese and going on to borderline diabetic, you wouldn't want to tell them, hey, don't eat any sugary stuff and thing. That's not going to work. You're going to say, cut down your intake this week, come back to me, let me see what's going on. Then you take them off a little bit more, then you take them off a lot more, right? Now take them
That
off
make
all
full
out.
sense. That make full sense.
All right. Last week I said this. I don't know if you remember, Owen, but chain branches don't go on the first or the first carbon. This first carbon or this
Yes, you
first
did.
carbon.
And you also said that going forward you during the more we learn about it, I'm going to see why it doesn't go on it.
Mm-hmm. All right. In this case, you have a branch here because whenever you're naming compounds, you want to find the longest chain first. I'm going to use the same rope analogy or the tree. Let's use the tree trunk analogy because that's kind of easier. The tree trunk would be your longest chain, so the chain with the most carbon continuous, right? Then your branches would be whatever comes off of the main chain, all right? So in this case, you have 1, 2, 3, 4 carbons going that way. And if you decide to count 1, 2, 3, if you go this way. And if you come from this side, 1, 2, 3, 4 going this way. So let me do this. This way in blue, that's 4 carbons. If you decide to go as a straight chain like this, that's also 4 carbons. And if you decide to do this, that's just 3 carbons. So your longest chain is either the first straight chain or this blue chain here going this way from 1, 2, 3, 4. So that means that this group here could be a branch. If you take this chain, this 1, 2, 3, 4 chain as your longest, or if you decide to use this chain in blue here as your longest chain, then your branch would be this methyl group. 1, 2, 3, 4. The carbon with the three hydrogens. Clear? Not you, Owen. I know said it's clear for you. Anicia. Hello.
Yes, it's clear.
Oh, okay. All right, great. So now that you've gotten that clear, we're going to use the first one. We're going to use the first one that I was talking about as the branch. So the first one I circled. So we're going to take the branch as being this carbon chain here. And then the branch would be this here. Let's use that one. So you'd write for the condensed formula, CH3 for 1 carbon and the 3 hydrogens. Then attached to that is another carbon. So you put carbon, then the hydrogen, then in brackets indicate that there is a branch of CH3, right? Then you'd continue. There's another carbon, and 2 hydrogens attached to it, 1, 2. Then the last, CH3. Clear? Hello?
Clear,
Holy
clear.
Jesus. Yes, okay. Now, for ringed compounds, let's deal with an easy one. Let's do cyclohexane. C bond, C bonds, C bonds. So that's cyclohexane. What's the molecular formula for cyclohexane? Molecular formula tells you exactly how many atoms are in a compound. So like ethane, the molecular formula would be C2H6, right? So looking at the structure here, let me draw on the H's. The 2 H's here, because remember carbon can only make 4 bonds. So this would be 1 bond, this would be 1 bond. So it only leaves space for 2 more. So that's why it's 1, 2 hydrogens, all right?
Come here, give me a second. My mother is calling. Give me a second.
No problem. I'll just explain when you come back. So that's how we got the hydrogen, 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 hydrogen. So we're doing gravimetric analysis next week, all right? So,
Okay.
yeah. So the molecular formula for this would be C6, because there are 6 carbons. There are 6 carbons, 1, 2, 3, 4, 5, 6, right? And how many hydrogens? 12 is great. So cyclo.
C2H6 up there.
Oh, I was telling you that that was the molecular formula for ethane. I was just showing you an example of molecular formulae. So cycloalkanes, they have the same general formula as alkenes. All right. So the general formula for alkenes or formula is CnH2n, right? Where n is a positive integer, meaning a positive solid number. Integers are like 1.
I'm back.
All right, great. So I was saying, Owen, that the molecular formula for cyclohexane is C6H12, right? So not having, suppose you get a larger compound and you don't really want to draw this out in exam because you don't have any time for that. That's why we use shortcuts. So I was telling
Wait, 1 second. Wait. Repeat, please.
Okay, the molecular formula for cyclohexane, this compound here,
Yeah.
is C6H12 because it has 6 carbons and 12 hydrogens, right?
Right. Following you so far.
Great. So I was saying that cycloalkanes, like cyclohexane here, is it's a ringed alkane, right?
Yeah, starring alkene, yeah.
Yeah, so those are called cycloalkanes, right?
Alright, so
Have the same.
ring carbon structures are known as cycloalkanes.
No. Ringed carbon structures are called aryl compounds. ARYL. Remember I told you this earlier?
Yeah.
But ringed carbon alkanes called cycloalkanes.
Okay. Alright. So carbon ring structures are known as aryl compounds, while the alkene structures that are ring structures are known as cycloalkene alkenes.
Alkane.
Right.
Yes. So cycloalkanes have the same general formula as alkenes, which is CnH2n. All right.
Alright. Following you that much, yeah. Following you so far.
That is why where the N is a positive integer. N is a positive integer. What I mean by positive integer, a positive solid number. Now, remember, integers are like 1, 2, 3, 4, 5, 6, 0, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, right? No, it doesn't have a decimal point and thus cannot be written as a fraction. Or, yes, it can be written as a fraction, but let's not get into that. Because, like 6 is equal to 6 over 1, right? Hello? Okay. It wasn't hypothetical. It wasn't rhetorical. Well, hypothetical. It wasn't rhetorical. It was an actual question. All right. So, integer. It has to be a positive integer. Positive solid number. So either 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. As long as it is a positive integer, then it is very plausible to be used as the representation for n or substituted for n. So in this case, n is 6 in cyclohexane. So the formula would be C6H 6 times 2, right?
Yes, because 2n would have made it the 12.
Yes. You're going back very low, but may I hear you? Like, barely I hear you, but may I hear you? All right, so I think that's clear. As per the condensed formula now, the condensed formula for ring structure is basically them rings. So like this 1, 2, 3, 4, 5, 6. So this is the condensed formula for cyclohexane. Okay. Okay. And with the circle inside, that's the condensed formula for benzene. So ring structures, you actually draw the rings just like that without the the carbon atoms and the hydrogen atoms being shown for the condensed formulae for ring structures. Clear?
So for the structural formula, we have to ensure that we draw like a pentagon. Well, this is what what's that called? Hexagon? One, two,
Displayed formula
yeah, the
ON.
displayed
Both
formula.
both are
I
structural.
was trying to remember what shape it was. If it was a hexagon, it's a hexagon because you have 6. So basically, you draw a hexagon and then you would highlight that the hydrogens are bonded to the carbon, right?
Mm-hmm.
But for the condensed formula, what you do is you just draw, well, in this case, a hexagon with a circle inside of it, and that would be that.
Benzene. That's benzene. Though if without the circle, that's cyclohexane.
Okay. And in our syllabus, we only required to know benzene and cyclohexane.
right?
No, sis.
That's it. All right.
Oh
Sorry.
Lord, Owen,
So hold up. This 1, 2, 3, 4, 5, 6. This hexagon, right?
Mm-hmm.
That's the displayed or the condensed structure. The displayed, right?
Hold on. Which one are the hexagons? This over here?
Below ethane. Yeah.
Okay, yeah. This is the condensed formula, yeah.
Oh, condensed formula.
And this over here is the displayed formula. Remember, the displayed shows the actual bonds.
Oh, okay.
And the atoms. The criteria for the displayed, it has to show the bonds, which are the lines here, and the atoms themselves. So hydrogen and carbon, all right?
So it is the condensed, the one without the bonds is the condensed formula for when I'm
Hexane.
alkene. Oh,
Hexane. Cyclohexane. This one is specifically cyclohexane. Clear?
okay. Thank you.
Okay. Any questions? Any more?
And the one with the circle in it is for
Benzene,
okay.
because it's indicating the double bonds.
Just benzene.
Yeah. So that's clear?
Yes, it is.
Okay, so I'm going to end this portion of the video and then start the other part. All right.